Next, we will talk about magnetism, and in this section, we will talk about what are magnets, how magnetic fields work, and uh, what are the basic applications of magnetism in our day-to-day life. A magnet is simply a material that produces a magnetic field, and if you have ever played with magnets, you probably have felt that there are areas where the force you feel the attractive force on magnet are very strong. The area where the forces are strongest are called poles, and all magnets, no matter how they are shaped, have two poles. Whether it's a circular magnet or a rectangular bar magnet, all magnets have two poles, and these poles are namely called north pole and the south pole. And for example, if you have a magnet, and if you break a bar of magnet in half, you don't get an isolated north or south pole. Rather, you will get two new magnets, each with its own north and south pole. So if you for example, you have a magnet, north pole, south pole, you break it into two pieces, then you will have two separate magnets with north pole and south pole, instead of having a piece with north and south pole. So this is not what we will get. Rather, we will get two separate magnet with its own north pole and south pole. And a basic property of magnets is that unlike poles attract each other, and like pole repel each other. For example, if you see here, north pole and south pole, we have attractive force. South pole and north pole, we also have attractive force. And then north pole and north pole, we have a repulsive force. And south pole and south pole, we have a repulsive force. And we should also mention that the magnetic field are strongest at the poles of a magnet. And so we talked about a magnetic field, and then we should also clarify that what makes a magnet a magnet. A magnet, the answer to what makes a magnet lies in the structure of the material. Every single atoms, we know every matter is the building block of every matter uh, is a collection of atoms, right? And every single atom acts as a tiny magnet. This is because electrons are moving around the nucleus. So we talked about it in the last video. We have in an atomic structure, we have a nucleus where there are protons and neutrons, and then we have these cells of electrons where it's orbiting around the nucleus, and this electrons moving around the nucleus, they have an intrinsic property called spin. So the electrons are orbiting as well as spinning, and this movement around the orbit and the spin essentially create tiny circulating electric currents. As we know, when charges are moving, we will get electric current. So this movement of electrons creates a circulating electric currents, and because of this electric current, we will get a magnetic field. So in a summary, we can say that wherever there is a electric current, we will get a magnetic field, and this in every atom, because of this movement of electrons, we will get electric field resulting in a magnetic field. In most materials, in most of the materials, the magnetic field of these billions of tiny atomic magnets point in random direction. We can see here, and there are these small magnetic fields are oriented randomly. These atomic magnetic fields are oriented randomly, and because they are oriented randomly, they cancel out each other, and this is an example of how unmagnetized materials. And in simple word, unmagnetized material have all these atomic magnets oriented randomly, and this magnetic field is cancelled each other, resulting in overall non-magnetic material. However, in materials like iron, nickel, cobalt, where we materials which we call magnetic materials, the atomic magnet are grouped into regions called magnetic domain. And when the materials is magnetized, this magnetic field of the atoms within this domain, and often this domain itself will align in the same direction. So we have small domains of this magnetic fields, and in these small domains are in the simple version, we can say all these small atomic magnets, they orient in the same direction, and they align, all the magnetic fields are aligned in the same direction. And this alignment creates instead of cancelling like in random orientation, this alignment of atomic magnetic fields uh, are create this creates a strong unified magnetic field. And uh, the effect is of a small sorry the summation of all this small magnetic field will be a strong magnetic field, and we call it a magnet. And whenever we use a magnet to attract some magnetic materials like iron, or some other materials, the attraction the magnet attracts this other magnetic material by temporarily inducing this alignment in the same direction. So what it does is, when we expose these magnetic materials in the magnetic field of a permanent magnet, this magnetic field will align all these atomic magnets in same direction, creating a stronger magnetic field, and attracting the magnetic materials toward the magnet. And just like we learned about the invisible electric field around charges in last section, a magnetic field is the invisible area of force and that surrounds a magnet and exert a force on other magnets or magnetic material. And we can see here we have this magnetic field represented by lines like this, similar to what we did on electric field. And generally you will see this magnetic field represented by either capital letter B, or sometimes you will also see letter H, and mostly you will see a capital letter B. And sometimes you will also hear, instead of a magnetic field, you will also Here you will also call this magnetic field by the name B field. And in terms of the direction of this magnetic field, the lines always emerges from north pole and enter the south pole. If you see here, this is going from north to south, north to south, north to south, north to south, and so on. All this line will go from north to south, uh, and in terms of its strength, we can see at these poles, in the north pole and south pole, all these lines are in a compact form. They are very close. That's why the strength of this magnetic field is very strong at the uh, poles, because the strength of magnetic field is strongest when all these magnetic field lines are closest to each other, and as they get spread out, we can see here the magnetic field strength will get weaker, similar to what we saw in charge electric field. The electric field was strongest near the charge, and as it went away from the charge, the electric field was weaker. And one rule of magnetic field is that this magnetic field will never cross each other. You will always have this magnetic field, and they will never cross each other. And the standard unit for measuring the strength of magnetic field is Tesla, and it's generally written with the symbol T. And this magnetic field strength, this Tesla unit, was named after Nikola Tesla. And one fundamental truth about truth in physics is that magnetic fields are created by electric currents. So we should remember it, like whenever there is moving electric charges, or in other words electric current, so whenever there is electric current, we will get some magnetic field associated with the electric current. And this the this principle of electric current can help us define permanent magnets and electromagnets. Permanent magnets, as we just discussed, the moving charges are the electrons spinning and orbiting within the atoms, and if these electrons movements are aligned in the same direction, you get a persistent or a permanent magnetic field. And the materials with such magnetic fields, we call it magnets. And the magnetic property of this material, this sort of materials, are permanent, and as the name suggests, we call it permanent magnets. And then we also have electromagnets, and this electromagnet is where electricity and magnetism truly connect to each other. Like in a lot of motors, generators, we see these coils everywhere, and this the electromagnet is where we will get an actual connection between electricity and magnetism. If you pass an electric current through a wire, you create a magnetic field around that wire. Like we just said, whenever there is an electric current, we will electric current creating an electric field. We will get a magnetic field around that wire, and by wrapping that wire into a coil, we can see in example here we have a magnetic material, solid, generally an iron block is used as this solenoid. This material is wrapped with the wire and created a coil. Often we just said this material is made up of iron, and if we do so, we will concentrate and amplify this magnetic field of each wire, magnetic field created in each wire, forming a very strong and powerful electromagnet. Like we said, if we have a wire and there's a current flowing through it, we will get a electromagnetic field around this wire. And this, if we create a coil of this multiple coils of this wire, we will get a strong a strong electromagnet. And the huge advantage of an electromagnetic magnet compared to a permanent magnet is that the magnetic field of an electromagnet can be turned on and off by simply turning a switch on and off, and or in other words, by simply uh, changing the flow of current, whether the current is flowing or the current is not flowing. And we can turn it on or off, the magnetic property. And furthermore, we can also control the strength of this material, the magnetic field, by changing this number of coils, or the power supplied, current supplied from a battery or a electric source. We can classify magnets into three functional types based on how they generate and maintain their magnetic fields. The first one is permanent magnets, like we just talked before. These materials, like the simple bar magnet or refrigerator magnets we see in our we put it in our refrigerator, retain their magnetism indefinitely without needing any external power source. And in one word, we can say these magnets are always on. So these are permanent magnets. And then we have electromagnets. These are temporary magnets where a magnetic field is created solely by an electric current flowing through a coil. And these are these electromagnets are incredibly useful in applications like motors, relays, because they can be precisely controlled, and we can control the magnetism as well as the strength of the magnetic field, and we can simply switch on or switch off the magnetic field. And then we also have these temporary magnets. uh, these are materials such as soft iron or paper clip that can be easily magnetized when you place in a strong magnetic field, but quickly lose their magnetism once the external field is removed. For example, if you work in your electronics devices, and sometimes you will open your electric devices, and you will if you have a magnet, and if you rub your screwdriver in the magnet and just take it close to a screw, you can feel that the screwdriver will attract the screw, and you can use that property, the temporary magnet created in the screwdriver, uh, to put the screws in the screw hole easily. And after some times, this temporary magnet will return back to a normal condition. in other word, this magnetic atomic magnets will temporarily align in the same direction, and uh, after sometimes they don't have after sometimes they will uh, change to a random alignment. And one of the largest magnet we interact, not just one of the, but the largest magnet we interact with daily is Earth itself. The Earth behaves as a giant magnet, and this is why a compass works. So whenever we are using a compass, it shows the direction. It shows the north and south pole of, so north and south, right? And the compass, the basic operation, the working principle of compass is based on the Earth's magnetic field itself. The Earth's magnetic field is generated deep within the planet by the movement of molten iron in outer core. This motion of this molten core is known as a geodynamo, and this motion generates a massive electric currents with which in turn like we said, if there's a electric current, it will result in a magnetic field, and uh, the this movement of a molten iron in the outer core creates massive electric currents, and it results in uh, global magnetic field, and that create that's why Earth itself behave as a big magnet. And one thing we need to note in a compass, a paradox, is that the Earth's magnetic south pole is actually located near the geographical north pole, because the compass north end is attracted to the geographical north. uh, uh, we can see whenever you are using a compass, it always, the north pole, the compass north will show the orient toward north pole. But what we know about magnetic property is that uh, the same pole will repel each other, and unlike pole will attract each other, meaning if the north itself was a magnetic, the north pole of Earth was magnetic north, then the compass, the magnet on the compass and the Earth's magnet, uh, if they have the same polarity, they will repel each other, and that's why the Earth, the we can, that's why we can say that the Earth's magnetic, and we should also note that this magnetic fields that Earth's outer core creates uh, acts as a gigantic magnetic shield, protecting Earth from a continuous stream of harmful charged particles emitted by sun, known as solar wind. And this magnetic field created by this giant uh, giant magnet deflects these particles around the around the planet, keeping us safe. As we know, this electric field and magnetic field interact with each other, and because earth itself is a very big big magnet, earth is surrounded with a magnetic field, and this magnetic field help the planet as a, help the planet to shield from harmful charged particle called solar wind. And the way a material interact with an external magnetic field, we can define materials in three categories, namely diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials such as water, gold, copper are actually weakly repelled by magnetic field. They have no permanent magnetic moment, and magnetic field induces a small opposing magnetic field within the material. We can see here in an example from a paper. We can see here when there's no magnetic field, this is the first condition when there's no magnetic field, and in the second condition the magnetic field is oriented in this direction. However, the atomic magnetic field is oriented in opposite direction, resulting in a small opposition between magnetic field and these materials. And then we have paramagnetic materials, and these materials like aluminum, oxygen, titanium are weakly attracted to magnetic field, but the effect is temporary. Their atomic magnets only align when the external field is present, and they lose magnetism quickly when the magnetic field is removed. We can see here the magnetic field, and as we apply um, as we apply this magnetic field, they are oriented in the same direction as magnetic field. And then we have a ferromagnetic field. Here we can see ferromagnetic materials. All these magnetic particles are oriented in the same direction, and once you apply the magnetic field on these materials, all this magnetic field will oriented in same direction as the magnetic field, resulting in attraction between magnet and ferromagnetic material. And some of the examples of ferromagnetic material are iron, cobalt, nickel, uh, and these are the materials that can be permanently magnetized because of how easy these magnetic atomic microscopic magnets are, uh, how easy uh, how easy it is to align this microscopic magnetic field in same direction. So in other words, magnetic permanent magnet are made out of ferromagnetic materials. And finally, we should also talk about some of the application of magnets and this magnetic field, because magnetic principles are used in all these modern technologies. And for example, electronics and home appliances, magnetic components are crucial in this kind of applications. For example, in speaker and headphones, magnets are used to convert electrical signals into sound waves uh, by controlling piezoelectric sensors, and we also have electric motors that power everything. For example, blender, vacuum cleaner, etc., which converts electric power into mechanical motion. And then we also have transportation. Electric motors in, for example, electric vehicles are based on electromagnetism. uh, we also have application of magnets in medicine, for example MRI, which stands for magnetic resonance imaging. As we see, the whole name of the device is based on a magnet. And these MRIs are one of the strongest magnet that's used in medical devices. And this magnetic field is strong. This extremely strong magnetic fields are used to create detailed image of human bodies. And on top of that, magnets are used in massive generators to convert mechanical energy into electrical energy, and to operate this industrial equipments. Similarly, magnets are also used to convert, for example, water current to convert it into hydroelectricity.